Hello again, welcome and thank you for joining me for another video, 11.2, the second lesson on Year 13's integration for Edexcel's A-level maths course. So 11.1, we've just gone through the formula book in quite a bit of depth, fairly hard going. Eventually you will need to be very familiar with those results, even though you are given them in the formula book. But spotting them and identifying them in advance is going to be crucial for A, saving you time in the exam, rather than having to frantically check the formula book, am I told that or am I not, and having to worry about it all the time. And as well, just in terms of fluency and speed, you will get better and more confident the more results you can commit to memory. And the best way of doing that is to just practice incessantly, really. And on the topic of practice, here's some warm-up questions for you to try. So the first question is differentiation, so you need to be comfortable with chapter 9. Question 2, we're going back to expanding and simplifying and then finding an integral using year 12 skills. And in question 3, we're going to recap the binomial expansion and then show an equivalency between question 2b and 3b. And then we're going to think about later today how we can do this in a simpler way using a technique I'm going to introduce to you this lesson. Okay, so pause the video now and try these on your own. When you're ready to see the solutions, press play. And hopefully you'll be more or less on the right lines. Okay, well, let's get to it. Let's have a look at question 1 of a warm-up. We need to differentiate these with respect to x. So ln 5 ln 2x. Sorry, 5 ln 2x, I mean to say. So how are we going to do this one? Okay, well, a common mistake would be to say that ln of 2x, if you differentiate it, goes to 1 over itself. But actually, ln of kx will always just differentiate to just 1 over x. And so this here, ln 2x will differentiate to just 1 over x. We've got 5 lots of these, so it's going to be 5 lots of 1 over x. So d by dx of 5 ln 2x is just going to be 5 times 1 over x, which of course is just a 5x. If you're thinking, well, why isn't it 1 over 2x? And what you could do, just to consider why this is the case, if you wanted to, we could actually expand this original function. In other words, I'm not saying do this all the time, but just to convince yourselves, 5 ln 2x is the same as 5, then using the laws of logs, ln 2 plus ln x. ln 2x can be split up like that, you see, which of course gives 5 ln 2 plus 5 ln x. When you differentiate it, that constant will disappear because 5 ln 2 is just a number, and 5 ln x, I'm hoping, is more convincing to you that that will differentiate to just 5 over x. So if you forgot or a bit rusty, that's why it's the case, and hopefully that's convinced you why the answer is 5 over x for that derivative. 1b, differentiate sine a third x. Sine differentiates to cos, but because it's sine of a third x, we can say that d by dx of sine a third x, that third comes to the front now, then we get cos of the same angle. And the last one for question 1, differentiating sec squared 5x. Let that equal, I would suggest, u squared. I'm going to use a chain rule here. So I'm going to set u to be sec of 5x. So if I do dy by dx, or just d by dx of sec squared 5x, I can say that's dy by du, basically just calling this y essentially. Dy by du multiplied by du by dx. So if y is basically u squared, differentiate that with respect to u, that gives us 2u. Then we need to remember the results from chapter 9. If I differentiate sec with respect to x, what we need to remember ideally, and although you're told this in the formula book essentially, sec will differentiate to sec tan. But because it's sec of 5x, what we're going to get there, that 5 is going to come to the front, and we get 5 lots of sec 5x tan 5x. And so the dy by du is for 2u, and the du by dx, differentiating sec 5x, goes to 5 sec tan. Then remembering that u actually was sec 5x and putting this back in, 2 times 5 of course is 10, u is sec 5x times another sec 5x, gives us sec squared 5x multiplied by tan 5x. So that's question 1 wrapped up. Let's have a look at the warm-up question 2 next. Question 2, capital I, called it I to stand for the integral. I just stands for the integral of 2x plus 1 all cubed with respect to x. For part A, what we need to do is to just expand and simplify 2x plus 1 all cubed. You can do this in whatever way you want to be honest. What I'm going to do here, I'm going to do 2x plus 1 squared and then multiply that by 2x plus 1. So 2x plus 1 all squared, whoops, forgot the bracket, is 4x squared. Take the product and double. 2x times 1 and double it is 4x, and 1 squared is 1. So all of this multiplied by 2x will give me 8x cubed. 4x times 2x is 8x squared. 1 times 2x is just 2x. Then all of this times by just 1, I'll just get 4x squared plus 4x plus 1 again. By the way, if you wanted to use the binomial expansion or the grid method or another way of doing it, that's absolutely fine as long as you agree and you're confident whichever method you're using to do this for. So I've got 8x cubed, x squared's 8 plus another 4, I've got 12x squared, then 2x plus 4x is just 6x's, and then just of course for 1. Now I need to now evaluate that I, actually integrate this. Now I've got it all in polynomial form. So therefore I can say now I is the same as the integral of 8x cubed plus 12x squared plus 6x plus 1, all with respect to x. So all I've done here is essentially just rewritten 2x plus 1 cubed in expanded, easier year 12 looking form like this. Although I'm hoping you're thinking this was, a bit of time to do that. That took us a couple of minutes to get it into this form. I wonder if there's an easier way I might show you later. Anyway, doing this first of all, 8x cubed, add 1 to the power, goes to 8x4, then divide by the new power. 8x4 divide by 4 will give us 2x to the 4. This one becomes 12x cubed divide by 3. That'll give 4x cubed. 6x will go to 3x squared. Sorry, what am I talking about here? Sorry, yeah, 6x will go to x squared, and then I'm going to divide that by 2. Yeah, that will give me 3x squared. Apologies. And then integrate the 1 will give me x. Then, of course, the constant of integration is going to call c. So that's the integral where c is just an arbitrary constant of integration. Now I'm going to link this with question 3. So question 3 says by using the binomial expansion or otherwise find 2x plus 1 to the power 4. So I'm just going to just recap the binomial expansion from year 12. And so 2x plus 1 to the power 4 all expanded will be 4 choose 0, 2x to the power 4, 1 to the power 0. And then this number is going to go 1 higher each time. This will go 1 lower, that'll go 1 higher. But this plus that will always equal 4. I'm putting equals. So then plus 4 choose 1, 2x cubed now, and then the 1 will be to the power 1. 4 choose 2, then 2x squared, 1 squared, and 4 choose 3, 2x to the power now only 1, and then 1 cubed, and finally 4 choose 4, 2x to the 0, 1 to the power 4. My habit is to write it out the long way. There are shortcuts to this. For example, the last term will always just be that number to the power 4. The first term will always just be 2x to the power 4. But writing it like this, I think you can easily see the pattern of how these numbers are changing. But anyhow, this first one will become 16x to the power 4. 4 choose 1 is 4. You can do this on your calculator, 4c1, multiplied by 2x cubed. Well, 2 cubed is 8. 8 times that 4 gives 32. So we've got 32 now, x cubed. And then the x squareds. 4 choose 2 is 6. 2 squared is 4, so 6 times 4, that gives 24x squared. This one, 4 choose 3 is 4. 2 to the power 1 is just 2, so 4 times 2, that's going to give us 8. So we're going to have 8x's. Then finally this one, it's going to be 1 to the power 4, which is just 1. So that's what we get for 2x plus 1 to the power 4. Well, expanded out, we get this expression. Now, part B, it says compare that to the question for 2 part B, showing that I can be also expressed as 1/8 2x plus 1 to the power 4 plus c. So if I just recap what we had from 2b, so from 2b, we saw that I was actually equal to 2x to the power 4 plus, what was it now, just thinking? It was 2x to the power 4, and then we had 4x cubed, then it was 3x squared, then plus x plus c. So now we can see that 2x plus 1 to the power 4, let's put this little thought bubble here. So I want to show that 1/8 of this plus some constant is one and the same as what we had from 2b. And so if I just do 1/8 of 2x plus 1 to the power 4 now, I'm just going to take what's in the yellow and find 1/8 of it, basically just dividing all terms by 8. So I'm going to have 2x to the power 4. 32 divided by 4 is 4, so I get 4x cubed. 24 divided by 8 is 3, so I get 3x squared. 8x divided by 8, of course, is just 1x. 1 divided by 8 is 1. So then I get 1/8. Now at this stage you might be thinking, well, that's not quite the same. It's almost the same as what I had from 2b. The 2x to the power 4 matches, x cubed match, 3x squared match, the x matches. But this arbitrary constant of integration, of course, isn't necessarily the same as 1/8. But we want to show is the same as 1/8 of this plus some arbitrary constant. So this 1/8 basically can match to c, but by just putting in, for example, a different c, because c is just an arbitrary constant of integration. So essentially, this bit here is the same as that. 1/8 is just a constant, so constant plus a constant is just a new constant. So we could have just termed our constant a different letter, for example, a d or a k, but essentially we've shown that it can be written in 1/8 2x plus 1 to the power 4 plus some constant there. So therefore, we're going to show an easier way of doing this. The integral I can be written as 1/8 2x plus 1 to the power 4 plus c, because we've shown that 2b and 3a are exactly the same thing. The only thing that is different from these is that one, when I do 1/8 of it, is 1/8, and that isn't the same as that constant, but because the constant is arbitrary until we know the definite limits, That's absolutely fine. So essentially it's in exactly the same format, so we've proven that. Let's now have a look at a very crucial concept now called u-substitutions. So how to integrate functions where you've got a function not of just x or even a function of kx, but a function where you've got some constant times x plus b. And it could be that you've got a function like this, itself to the power of n, where n is some constant. So how would we integrate something like this? So what we've done so far, we've begun to familiarise ourselves with the standard integration results found in the formula book. So these results are all actually in terms of f of kx. However, what if we needed or wanted to integrate something like this, where it's f of ax plus b, or even f of ax plus b to the power of some n? The book tells us to use a method of balancing the constant, which is absolutely fine and will always work for these forms here. I'm going to show you a different way of doing this for a couple of reasons. The primary reason is this method is going to crop up later in this chapter anyway. So the first thing I'm showing is introducing this method in advance, so when it comes to introducing it fully in the book, you've already dipped your toes into the water and know a bit about it in advance. Secondly, I think this method is just a slick way of doing it. So what is this method? So the method I'm going to show you here is called a u-substitution. Essentially all this means is we're going to replace ax plus b with a simple u by setting u to be the same as ax plus b. So we're going to take something that looks slightly awkward and make it look simpler by simply using a substitution and essentially using algebraic manipulation and our knowledge of calculus. So the method and the logic behind it, I'm not going to go into too much detail now. We're going to crack on with practice as our main focus. If you do want to have a bit more explanation though and understand it in a bit of a richer detail, I've linked another video to it. The QR code is here. If you've got the notes, I'll put a link in the description to this video, and it'll also link within the video itself so you can click on it with your thumb or finger if you're watching it on your phones. So what's the procedure? How does it work? Just doing it. How would you do it to get your marks? That's what you're interested in, I suppose. The understanding's here. How would you just do it? Well, the procedure, set u to be ax plus b, so just replace ax plus b with the letter u. Step 2, find du by dx. Differentiate u with respect to x, which of course will just be a. Step 3, replace dx in terms of du using step 2. Step 4, now integrate the function in terms of u. Then finally, because u is just our substitution and the original function would have been in terms of x, put it back to what it was in its original form. So step 5, rewrite the solution in terms of x. So when can you use this, or when should you use this u-substitution like I'm explaining in this case? There's 3 main ways. So when to use, you can always use this method when n is exactly equal to 1. Try this for any function, you'll get a good result. If n is bigger than 1, I'd only go for this method if you're talking about integrating something to the power of e. So k is some constant. If you're integrating e to some power ax plus b, and that's to the power n, you can use this method. I'll show you how in an example in a moment. And another time when this method will come up trumps and will work great is if you have a function where the power n is to the minus 1, you've got some constant multiplied by not a function of ax plus b, but just a linear expression in its own right, where the function is just simply something linear to the power minus 1. I'm going to show you how that works in a moment. So it doesn't probably make too much sense yet because it's all abstract. So let's put it into actual practice, then you'll see hopefully how nice this method actually is. So worked example. This is from the notes. So is there an easy way of integrating 2x plus 1 cubed? Well, yes, there is. Let's use this method here. So ax plus b is 2x plus 1. So what we're going to do here, step 1, we're going to set u to be 2x plus 1. So let u be 2x plus 1. And step 2, find du by dx. So du by dx will just be 2. So that's step 2. I won't do these steps written on all the time, but just to show you for now where these steps are coming from. So then I need to replace dx in terms of du. So that's dx. If I were to just think about this as one fraction equaling 2, I've said this before, calculus derivative notation aren't actually fractions, but as a shortcut, we can treat them as fractions essentially. So if I multiply both sides by dx and then divide by 2, you can hopefully see that dx is going to be du divided by 2. So now I've got dx in terms of du. That's step 3. So dx is one and the same as du over 2. Step 4, we can now integrate this thing with respect to u. So for step 4, this now becomes not 2x plus 1 cubed, but because I'm saying u is 2x plus 1, whoops, wrong colour, I can say it's the same as u all cubed with respect to dx. But because we now know that dx is the same as du over 2, I can just switch dx in terms of du over 2 like so. So 2x plus 1 cubed just becomes u cubed, dx is now just du over 2. So that over 2 is obviously just a half. So as a constant, I can move a half to the outside, but I'm just integrating u cubed with respect to u. Now, doesn't that look much easier? It does look easier, and it is easier. So now integrate that as you would do in year 12. Integrating u cubed with respect to u. That's the same as integrating x squared dx. So the 3 will go to 4, and a divide by the new power. Plus, of course, the arbitrary constant of integration. Then neaten up, a half times a quarter is 1/8. Then I'm going to have u to the power 4 plus c. And step 5, put it back in terms of x. So what was u in terms of x? U is 2x plus 1. So I've got 1/8, 2x plus 1 all cubed plus c, which is what you saw in warm-ups question 2 and 3. And hopefully I've convinced you that's a much slicker way. With practice, you can do this in seconds. Warm-up question 2 and 3 will always take you a matter of minutes, unless you're a genius. Sadly, I certainly am not. Question 2. Let's integrate 1 over 3x minus 2 with respect to x. So what I'm going to do here, first of all, I'm going to say that's one and the same as 3x minus 2 all to the power of minus 1 with respect to x. So now I'm going to call that my u. So I'm going to say u is 3x minus 2. Therefore, du by dx is 3. So therefore, in terms of du, dx is going to be du divided by 3. So this integral here is now going to become, of course, 3x minus 2. I'm going to call that u, so that's going to be u to the power minus 1. And then dx is going to be replaced with du over 3. So over 3 is obviously just 1/3. So take the 1/3 to the outside. Now integrating u to the minus 1 du. You can leave it as u to the minus 1 if you want. If I write it as 1 over u, though, that will maybe just jog your memory. How to integrate 1 over something with respect to itself. Hopefully, that's reminding you that that's going to now be a log. It's going to be ln mod u. So that's going to give us 1/3 ln modulus of u, plus of course a constant of integration. But what was u? Of course it was 3x minus 2. So putting that back in, that gives me 1/3 natural log modulus of 3x minus 2, all plus c. And so in terms of these notes in this table, that's when essentially integrating a ax plus b expression to the power minus 1. So again, that's an example of how it can be used in that particular case. You'll have something in terms of ln of a function. Number 3. There's a couple of ways of doing this. So how to integrate e to the 3x plus 1 all to the power 4 dx. I'll show you the slow way first, and then the quicker way. So, slow thing first. What I'm going to say here, I'm going to say that's the same as e to the u to the power 4 dx. So basically I'm just going to call u to be 3x plus 1. So then if I take the derivative of u with respect to x, du by dx is going to be 3. And so from that, I can see that dx is going to be du divided by 3. So this becomes e to the u to the power 4. U times 4, of course, is going to be 4u. But then dx is the same as du over 3. So I've got e to the power 4u multiplied by du over 3. So that's going to be the same as 1/3 of the integral of e to the 4u du. So if we integrate this, what will happen, of course, I'll have 1/3. That constant will stay as it is. If I integrate e to the 4u, obviously integrate e to the power of something, the power stays stuck, so I'm just going to have e to the 4u still. Not myself much space. Sorry about it being a bit cramped. Should have made myself more space. So that 4, I'm going to end up dividing by it. So it's going to be 1/4 of e to the 4u plus some constant of integration. And then neaten it up, 1/3 times 1/4 is going to be 1/12 e to the 4u. Now, u, of course, was 3x plus 1. So 4 of u will be 12x plus 4. So I'm going to have 12x plus 4, then all plus c. So that's a slower way of doing it. That's a fairly brainless, mindless way. I don't say about any disrespect. That's the sort of thing I would do myself and then kick myself after. So a quick way, of course, is just to remember that what you learned from year 7, year 8, year 9 is still relevant. This thing here, simplify it first of all. So I've got a power to a power. That's just the same as e to the 12x plus 4. So you can simplify the power straight away if you want to. And so using this here, for this one, what I could have said u can be instead 12x plus 4. In this choice, I could have said that du by dx, of course, would be 12. So therefore, dx is the same as du divided by 12. So then, I'm basically integrating, because I'm calling it now, I'm calling this thing here 12x plus 4, I've called it u. So if I now integrate e to the u with respect to x, but my dx now is du over 12, I'm going to have e to the u times du over 12. So I've got 1/12 integrate e to the u du, integrate e to the u will stay as it is. So of course I'm just going to have 1/12 e to the u I said was 12x plus 4, plus of course the arbitrary constant of integration, which we must not forget. So that's equivalent to this. Either way around gets you the correct result. Question 4, we've got a definite integral to consider, but fear not, it's going to work in almost exactly the same way as before. So we're going to integrate from between a quarter pi down to an eighth pi of sec squared 1 minus 2x with respect to x, giving answers to correct to 3 significant figures. Now, this one here, we do need to remember our standard results, or at least be familiar, or be thinking that this might be one to check the formula book for. A mistake here would be to use the u-sub and not realise that sec squared is one of these standard results. But sec squared actually is a standard result. If you integrate sec squared, it's going to go towards 10. Okay, so as a very sort of shorthand reminder, that's not very mathematical, that's just me just trying to jog your memory. Sec squared will go to something in terms of 10. So bearing that in mind, we can now approach the u-sub cautiously and be thinking that, well, that's our linear function 1 minus 2x. So let's go for u being 1 minus 2x. And if that's the case, of course, du over dx will just be minus 2, and so dx is du over minus 2. And so this now becomes the integral from pi over 4 to pi over 8 of sec squared u. And then du, we can put in to replace dx. Our dx, we can now say is the same as du over minus 2. Put the minus 2 to the outside, it's a fraction, so it's minus 1 over 2, minus a half, the integral between pi over 4 and pi over 8 of sec squared u du. Now, sec squared, like I say, goes to 10, and so this is going to be the same as minus a half of tan u in between the limits of pi over 4 and pi over 8. Now, looking at these notes, I did say to rewrite the solution in terms of x. So we can switch back in terms of x now, actually, because we're integrating these limits relate to x limits, not u limits. And so remembering that u is, whoops, wrong colour. Remember that u is 1 minus 2x, I can now put this back in again. So tan u just means tan 1 minus 2x in between these limits. So if we put these limits in now, so we've got minus a half. So tan 1 minus 2x, 2 lots of a quarter pi is going to be a half of a pi. Then minus the lower limit. So then it's going to be 1 minus 2 lots of an eighth of a pi. 2 lots of an eighth is a quarter, so it's going to be minus a quarter pi. So it's just a case of actually evaluating that using a calculating device. The street name is often called a calculator, or a calc if you want to be super cool. So, yes, let's just fill this in, and then I'm going to show you how you can use your calculator to check. So, we do minus a half, brackets, make sure you're in radians, of course. By gosh, make sure you're in radians, otherwise you're going to be in for a world of hurt. So then it was tan of 1 minus pi over 2. So then we do fraction button, shift, alpha, no, shift there, pi over 2, and then close brackets, then minus tan of 1 minus pi over 4. Close brackets again, and we should get 0.4300 and so on and so on. But because we want it to 3 significant figures, we're going to curtail it at 430. So our solution is 0.430. So last but not least, I'm going to now show you how a new style integral, as I call them, could be used to give you a question like question 4 in a way. Question 4 would very, very unlikely be asked because the examiner would know. You could just use it on your calculator. So a question would probably never be asked in this form. A question which might be asked similar to this in an exam style is worked example 5. So, given that the integral between -1 up to k of 3 over 2x plus 10 with respect to x is 3 over 2 ln 5, find the value of k. Well, let's see what we can do here. What I suggest we can do, first of all, is to simplify the integral. First off, what I'd suggest here is 2x plus 10 on the bottom. If you can simplify first, do so, is my general strategy. So I can factorise out a 10 on the bottom of this. So I can set the same as the integral from k to -1 of 3 over 2 lots of x plus 5. By the way, if you didn't factorise out the 2, don't worry so much. You can still use a u-substitution, putting u to be 2x plus 10. That's fine. But just doing it like this, it's just a slightly slicker way, I personally believe. So if I write it like this, what I can then do is I can now see that this is now 3/2 of 1 over x plus 5. So I can take that 3/2 out as a constant. We've got it between k and -1. And now because it's x plus 5 but 1 over it, I'm going to say that's the same as x plus 5 to the power -1 dx. So now my u sub, I can replace u with x plus 5, and dx I can switch for du in a second. So if I just let now u is x plus 5, so then du by dx equals 1. In other words, du is one and the same as dx. So essentially, knowing that, what I can do now is go on and actually solve. That didn't work as nicely as I wanted to. What I wanted to do is just box this off. There we go. So from this, we can now proceed. So this integral, I've got 3 over 2, integral from k to -1, x plus 5 I'm going to replace with u, because I said that u was, of course, x plus 5. So I've got u to the -1, integrating with respect to x, but of course du is the same as dx. So I can say it's u to the -1 du from what we found out here. Du is the same as dx. Now, of course, you should know now, if I integrate u to the -1 with respect to u, essentially 1 over u du, I'm going to get ln mod u. So that'll give me 3 over 2 ln mod u in between the limits of k and -1. So if I were to do that now, that's going to give me 3 over 2 now, of course, u is still needing to be in terms of x. So what I'm going to do first of all, actually, I'm just going to rewrite this in terms of x again. So u, of course, was x plus 5. In between k and -1. So again, that is going to give me 3 over 2. Now ln of x plus 5. So inputting x being k, that's going to be ln of k plus 5. Now, because k is a higher limit, and I'm adding 5, the implication here is k is going to be a positive constant. So I can actually get away with not using the mod symbol. I'm going to just put in brackets k plus 5. then minus ln minus 1 plus 5, which of course is ln 4. Now, because we've got log of one thing minus log of another, I can combine that into a single log using laws of logarithms. That's going to give me ln of this thing here divided by 4. But we're told, so if you look here, we're getting it close. 3 over 2 matches ln, ln good, so we know on the right lines. But this needs to be ln 5. So essentially, that ln, what we've got here, that needs to be 5. So matching bits and pieces together, we can hopefully deduce that therefore, k plus 5 over 4 must therefore be 5. Now, to finish off, we're going to solve, after all that hard work, we end up with a very simple sort of year 7, year 8 style equation. So it all parcels together. Maths is maths is maths. It's all relevant, which is one of the beauties of this. So times both sides by 4. K plus 5 needs to be 20. Subtract 5. K is going to be 15. Again, of course, if you had time in the exam, check this on your calculator by integrating numerically and checking that does give you the same as 3 over 2, 1.5 ln 5, and of course it will do. So what my suggestion now is for you guys to practice, practice, practice until your eyes and fingers bleed. Not literally, I'm joking. But in all seriousness, do try these. Page 297 to 298, exercise 11b in the splendid Edexcel Big Blue Book. Try your best, let me know how you get on, and never ever give up, to paraphrase a Mr. Churchill. Thank you for listening, and I'll see you in lessons soon. Take care. Bye-bye for now.